Chapter 3 is going to focus on polynomials, and today we're going to do an introduction to polynomials. So we're going to be identifying them, evaluating, adding and subtracting. We're going to classify them, which just means we're going to be naming them. We're going to identify real zeros from the graphs of polynomials. So we're going to start off by talking about the degree of a monomial. So remember, a monomial is one term. That's what that prefix mono means. Have you guys ever heard somebody say, "Oh, we're gonna go mono-e-mono"? Like sometimes in like fighting movies. I don't know. Maybe in Cobra Kai, do they say that? Mono-e-mono. We're gonna fight one-on-one. So if it is a monomial, you are gonna find the sum of the exponents of the variables. Okay, so if it's just one term, you're going to find the sum of the exponents of the variables. Okay, so we're going to look at example 1. So we're going to do 4 examples, the different types, and then we have to identify the degree. Identify the degree. Okay, the degree is just the highest exponent. Okay, so for part A, you only have one term, so the highest exponent in that case is what? 6. So the degree is 6, yes. We're going to skip over B because I feel that one can be a little bit tricky. Let's go to C. So in C, you have more than one exponent. Okay, you have more than one variable. What's the exponent on x? 1. And then the exponent on y is? 3. So the directions say that we find the sum. So the degree is? 4. Great. Okay, so do part D. So you guys can write down the answer. So we just talked about C, so that's going to be 4. Okay, so you have the exponent of 1 plus 3. Okay, and then for D, you're going to add those exponents together. So when you're looking at the exponents, you can see the 2 and the 3, but what exponent is hiding on the B? 1. Okay, so what did you get? 6. Yay! Okay, so 2 plus 3 plus 1 is how you're going to get 6. All right, now we're going to go back to B. What are you guys thinking? Okay? Yeah, it's either 1 or 0. Can anybody prove to me which one it is? What? What? So if you have anything to the 0 power, it is 1. That is true. This one just doesn't have a power to it. Yeah, Yetta, what are you thinking? Okay, so when we were doing this one, do you guys remember what the degree was for x? 1. Okay, so the degree, or the exponent on a variable is going to be 1. If it's a constant term, no, it's going to be 0. Okay, so the sum of the exponents are of the variables. Okay, so if there's no variable, okay, that would be like x to the 0 power. So it would be 5.6 times x to the 0 power, which would be 1, and then 1 times 5.6 would be the 5.6. So anytime it is a constant, there's no variable, so the degree is going to be 0. Okay, and then if there is a variable but you don't see the exponent, it represents a 1. Okay, for C and D, I just wrote out how we found those. Okay, when you're doing your homework, you don't have to write that out. You can just write the answer. I just want you to see why it's 6, right? So the 2 plus 1 plus 3. Okay, any questions for me with example 1? All right, let's keep it rolling then. Let's talk about the names of different polynomials. Okay, so these were monomials. We're going to look at some different polynomials here. So if the degree is 0, it is a constant term. And that's something we already know, right? We actually talked about that in chapter 1. We also talked about if the degree was 1, right? It'd be like x to the first power. That would be linear. And then if the degree was 2, that would be quadratic. Okay, so chapter 1 was all about the linear functions. Chapter 2 was all about the quadratic. So in the last column, we're just going to go over some examples. So an example of a constant term would be like the number 5. Okay, and then you have a semicolon. So I'm just separating. I'm just giving you multiple examples, okay? Negative 4 to the 2 is also a constant term. So that one's kind of tricky because you see the exponent, but the exponent is on a number, which means can I just do negative 4 to the second power? Yeah, what would that be? 16, okay? So that is still a constant value, okay? If there was an x there, I couldn't evaluate x to the second power. Okay, and then if it's linear, you might see something like x minus 5. That would be a linear example, or you could have 3x plus 2. So you can have a coefficient on x, that would be fine. Or it can just simply be x. Okay, but your x is always going to be to the first power. Okay, quadratic, we were just working with those a lot. Okay, you could have a quadratic polynomial that's just x squared plus 1. You don't have to have a middle term, but you can. X squared minus x plus 2, that's another example. Okay, now notice here, like this was a monomial, this is a monomial, but now we have some binomials here. We have a, what one's that? Trinomial. Okay, good. All right, and then does anybody know? Well, yeah, you guys should know 3. What's 3? What type of function? Cubic. Good. Okay, so if it's a cubic function, you could have 4 terms. We just call that a polynomial with 4 terms. Okay, so you could have a cubic that has x cubed plus 2x squared minus x plus 1. Or it could be shorter. It could be a binomial. It could just be x cubed minus x. Okay, do any of you know what the 4th one is called with a degree of 4? So when you think of things with 4, do you guys know the prefix of it? Yeah. Okay, so this is called a quartic, like a quarter. Or you know how there's 4 quarts in a gallon? 4 quarters in a year. Okay, so quartic. And then let's look at a couple examples of those. So you could have x to the 4th plus x cubed minus 1. You could have x squared plus 5x to the 4th. Do you guys know what the 5 is called? Yeah, it is. It's quintic. So like if a woman has 5 babies, right? Do you guys know those are called quints or quintuplets? Yeah, that sounds like a lot, doesn't it? I remember when I was growing up, there was like this toy, and it was like quintuplet surprise. It came with like 5 babies in it. So that's how I remember that 5 is quints, because of that toy. We had some good toys in the 80s. We had pound puppies. That was the same thing. It was like Velcro, her stomach, and you opened up, and then she had babies inside. You guys have any fun toys you remember playing with? Yeah, Legos, fidget spinners. Barbies, oh my gosh, I loved Barbies. Transformers, did you guys have Hot Wheels, Transformers? Yeah. I still have my Hot Wheels collection. All I wanted was like that rug that had the roads on it. When life was simple. Oh yeah, Thomas the Train. All right. So we already talked a little bit about this. So hopefully this feels familiar. So the monomial is one term, right? The mono. The binomial, like a bicycle, is two terms. Trinomial, tricycle, three terms. And then once it gets more than three terms, it's just going to be a polynomial with four or more terms. So if there were four, it'd be a polynomial with four terms. If it were six, it'd be a polynomial with six terms. Okay, so you're going to have to use these to write the name of different polynomials. And the degree for a polynomial is different than a monomial. So the degree for a polynomial is equal to the highest exponent. The degree for a polynomial is equal to the highest exponent. So that's different from the monomial where you were adding them together. Okay, because we're going to have binomials, trinomials, and then polynomials with four or more terms. Do you guys know how you can tell what the terms are? Like what separates them? What separates the terms? Mm-hmm.
Addition, subtraction.
Exactly, addition and subtraction. Good. So terms of a polynomial are separated by either addition or subtraction. So either a plus or a minus symbol. And that's how you can count the number of terms. Okay, so the terms of the polynomial are separated by a plus or a minus symbol. Okay, and then we're going to take everything that we just talked about on page 1, and that's going to help us with our example 2. Okay, so when you're ready, go ahead and flip it over. And then for example 2, the first thing we're going to talk about is standard form. Okay, so standard form is how terms are presented to you. So you may not have even realized that you already know what standard form is. Okay, so for example 2, we actually have a bunch of different things that we're going to be finding. And when they talk about standard form, do any of you think you could put that into words, what that means? Like, how would you know if something's in standard form? So we talked about standard form with the quadratic, the ax squared plus bx plus c. Do any of you think you can tell me what it means by the standard form? So if standard form for the quadratic is the ax squared plus bx plus c, the x squared term has to go first, right? And then what comes next? The x term and then the constant term? Yeah, Lizzie, you think you can tell me?
So it's like the highest exponent goes first, and then it goes into
Yeah, and then it goes in decreasing order. So you start with the highest exponent, and then it goes in decreasing exponent order. Okay. And you start with the highest exponent. Okay, great. All right, so let's talk about all the things we have to find today. So the first thing we have to do is rewrite each one so it's in standard form. So the highest exponent term goes first, and then it's decreasing exponent order. Then you're going to identify a bunch of different things. So you have to identify the leading coefficient, the degree, and the number of terms. And then once you've done all of that, you are going to name the polynomial. When you name the polynomial, there are two things that you're going to have to use. So when you name it, it is by the degree and the number of terms. So the polynomial name is always going to be compounded. So there's two of them. It's going to be a compound name. Okay, so the first thing we're going to do is standard form. So when I'm looking at these, I'm looking for the highest exponent, which is x squared. Make sure that you take that negative in front of the coefficient here. So negative 5x squared plus 4x plus 3. So notice that all the signs in front are going to stay to indicate whether it's positive or negative. Okay, and then, Kaden, what's the degree for this one? Oh, yeah, so, okay, for this one, you are going to, it's going to be the highest exponent only. So the highest exponent for this one is what? 2, good. And that's actually something I wanted to explain again. So if it's a monomial, that's when you're going to add those together. And then if it's not a monomial, you only have to look at the highest term, and that's going to tell you what your degree is. Okay? And then Gwen, what's our leading coefficient for this? Or if you're not sure how to find that, you can tell me. Okay, yeah, so the leading coefficient is always going to be in front of the term with the highest exponent. So if x squared is the highest exponent, what's the coefficient of that? Yes, yes, good. Okay, and then the name, like I said, is a compound name. So it's based on the degree, and it's based on the number of terms. Okay, so the degree is 2. Will you guys tell me what that name is? Nope. Quadratic, yeah. So the degree of 2 is quadratic. And then the second one is based on the number of terms. So how many terms do I have in this one? 3. So it is a trinomial. Great. Okay, so it is a quadratic trinomial because the degree is 2 and there are 3 terms. Okay, and then I'm going to have you guys try B, and then when I write these down, I just write it like this. SF for standard form, degree, I call it the LCO for the leading coefficient, and then the name. Okay, now for standard form, sometimes they're already given to you in standard form. Did you guys recognize this with B? Okay, so when you look at this in your textbook, if it is already written in standard form, you're just going to be writing 8x to the 4th minus 4x. That's fine. Okay, and then Luke, what's the degree for this one? Good. And then Danielle, what's the leading coefficient?
8.
Yeah. All right, and then Jack, tell me what you think the name is. Good. Quartic binomial. Okay, so quartic because the degree is 4, binomial because you have 2 terms, okay? Okay, go ahead and do part C if you haven't already. And then once you do part C, if you finish that pretty quickly, you can go on to example 3, part A. That's kind of tied into something we did in the last chapter. Alright, so the first thing we're going to do is write this in standard form. And Dane, will you tell me what your standard form was for this one?
X cubed minus 18x squared plus 2x.
Great. Alright, and then Ashley, what was the degree? 3. Lizzie, what was the leading coefficient?
1.
Yeah. Okay, Aiden, what was the name?
Cubic polynomial.
Okay, yeah, and then I have to go over the other part. So, cubic polynomial with 4 terms. I like Jeff giving you some positivity there. That's right. Alright, so cubic polynomial with 4 terms. Okay, so, and I saw that you guys put cubic polynomial. That's awesome. So you just have to tell me how many terms are. So if if it's 5 terms, cubic polynomial with 5 terms. If it's 6, just you can identify the number of terms. Okay, awesome. So now we are going to add and subtract polynomials. And then when you write your answer, you're going to write it in standard form. And I think that's something that most of you do naturally anyway. So when you add or subtract, when you guys combined like terms in Algebra 1, were there any strategies that you guys used for combining like terms? You guys do like special underlining? Okay. You can also like line them up. I'll show you a couple different ways. So I do like to underline in different ways. So when you're looking for these, I always start with what I'm given first, and I look for the highest exponent. So x cubed is the highest exponent. So I have 2x cubed and x cubed, so they both get the squiggle. Okay, and then remember this is like a 1 in front. So 2 and 1 is going to be 3x cubed. And now after the x cubed, I'm going to look for the x squareds. I only have one of them, which is the 5x squared, so that's going to go next. And I like doing them one by one like this. If you guys like underlining them all and then adding them together, that's fine too. And then negative x and 7x is going to make 6x. And then what do you guys think? Should we put some triangles in this mix? You guys like the different shapes? Okay, and then there's your final answer. Okay, so you're just combining your like terms. Now with the negatives, what do you have to remember to do? Yeah, do you guys remember that from 2.9? With the eyes? Good. I like it. Okay, so let's distribute that negative. I like to just write it underneath. And then I do the same process where I underline those terms. Okay, so go ahead and do B and C. Let's see how we do. and again, when I do this, I look for the highest exponent first. So if it's not the first one, I just kind of skip over that. Okay, so you should have negative 3x squared, and then you only have this one x here, so plus x, and then you have 3 minus 6, which is negative 3. Okay, and then I said I would show you another way to do this if you want. So the minus, when you distribute, if you want, you can line these up underneath. So sometimes I do that. So there's nothing to line up with the 5x cubed, but the negative y squared I can line up here. The plus 3 I can line up here. And then there's nothing to add the 2y to. But then you can just kind of add this straight down now. So you have 5y cubed minus 3y squared plus 2y plus 2. And that would be your final answer. So you could also think of it like that. Okay, so find which way works best for you. All right, ready to go to the back? We're going to talk some graphs, so we're going to need our graphing calculator. All right, so we're going to graph some polynomials today. The first part is actually stuff that we already know. So when we think about the notes are back. So when we think about the graphs of polynomials, okay, where can you find the real zeros on the graph? The real zeros are the same thing as what? The what? The x-intercepts, okay? So the real zeros are the x-intercepts. Remember, we talked about that when we were finding roots and zeros. So roots and zeros are just x-intercepts. Okay, so real zeros are the same thing as x-intercepts. Okay, so this is asking you how many real zeros are on the graph below. Notice I keep underlining real, because what other types of zeros have we been finding? Imaginary. But imaginary don't show up on the graph. Okay? So how many real zeros are on the x below? Well, what do I just have to find? Yeah, so how many x-intercepts are there? Let's find them. 1, 2, 3. Okay, so there's 3 x-intercepts, which means there's 3 real zeros. Okay, so the real zeros are the same thing as the x-intercepts, so you can look at the graph and you can see how many real zeros there are. Okay, you can't see the imaginary ones, you can only see the real ones. Okay, so what we're going to do is we are going to graph the polynomial function on a calculator, and then when you do that, like when you're doing that on your homework, I do just want a rough sketch of the graph, and we'll do that first part together. And then we're going to describe the graph and identify the number of real zeros. Okay, and we'll talk about what specifically that description has to include. Okay, so for part A, we have f of x equals 2x cubed minus 3x. So the first thing I want you to do is I want you to graph that in your graphing calculator. And if you don't have your graphing calculator with you today, come up and just trade me your device for one of mine. That's okay. Okay, so did you just have trouble putting it in the y equals? Are we good on that step? Okay, so we're going to go to y equals. Okay, and then when you're typing this in, the 2 is here. Oops, sorry. Okay, and then the x that we're using is right here, this button. So 2x. And then to get to the third power, you're going to use this button, so to the, and then third power. And then you are going to have to arrow down, and then it'll be minus 3, and then we're going to use our x key again. And then when you graph it, you should have like the standard window here. You can always go to zoom and then 6 to get the standard window. And then if you notice, like your see my calculator, I call it, it's going crazy right now. I can see it because it's going back and forth like, system overload. Okay, so I just have to turn it off and then turn it back on. You just got to reboot it. Okay, it still has my y equals in there. And then that's all it needed. Just needed a little break. Okay, so let's draw our sketch. So you have y and x. And then when I say a rough sketch, I just mean you don't have to put the points in, like you don't have to graph it point for point. We can see it's going up and then it kind of crosses through right here that at the origin. And then it goes back up again. Okay, so that's the sketch that I want. Okay, it's just a rough sketch there. Okay, and then for the description, okay, for the describe, there's a couple things that we're looking for. Okay, so this is what you have to include. Okay, so you're going to include, the first thing you're going to include is you have to explain how the graph increases. So how the graph increases. Or decreases. From left to right. And then the second thing is how many times it crosses the x-axis. And we'll do the first description together here. Sorry, I'll zoom that in here. Okay, so the two things we're going to include is how the graph increases or decreases from left to right, and then how many times it crosses the x-axis. Okay, so your description is always going to include those two things. How the graph increases or decreases from left to right, and then how many times it crosses the x-axis. So we really are just going to look and see what's happening here. And even if you just look at your sketch, right? Is it increasing or decreasing here? Increasing. Okay, so we can start the description the same every single time. And that is from left to right. Okay, the graph, and then you just have to tell me what it does. So the graph increases. Okay, and then once it increases here, it decreases. So the graph increases, then decreases. Okay, and then we get to another curve, and then it starts to increase again. So from left to right, the graph increases, then decreases, and increases again. Crossing the x-axis a total of, and then you're just going to tell me how many times. How many times? 3. Genius. Okay, so from left to right, the graph increases, then decreases, and increases again, crossing the x-axis a total of 3 times. Okay, which means how many zeros are there? 3 real zeros. So just make sure that you identify that they're 3 real zeros. Okay, and I know that we've already said this, but just to be very clear, the zeros are the number of x-intercepts. Okay, so for part B, I want you to draw your sketch, tell me the zeros, and then if you feel comfortable starting your description, you can absolutely do that as well. Okay, for B, we have g of x equals 2x cubed minus 2. Okay, so draw your sketch, you can start your description, identify the zeros. Alright, so once you guys graph this, actually I have a picture of it on the board, is what, it looks something similar to that. I'm going to show you on my graphing calculator. Now, depending on your calculator, and depending on your window, it can look like part of this is constant. This is the shape that you guys have, and what's happening here is it is increasing the entire time. I'm just going to zoom in. Sometimes if you zoom in, like, it looks a little bit flatter, like here. I'm going to zoom out. Okay, and so one way that you can double check that it is increasing the whole time is you can look at this trace, and the trace key will follow this curve. So let's start like at the left side. So I just press the straight button, the trace button. Did I say trace? Okay. And then we're going to just arrow to the right side and look at the y values. So it's -4, then -3, -2, and then you can see these decimals are moving slowly, but they do keep increasing the entire time. Okay, so we are increasing the entire way from left to right. And that is always going to happen with the cubic function. You won't stay constant. It's just with the technology, the pixels in the graph can look like it's flattening out there. Okay, but it's just increasing very, very slowly. Okay, so in our description, from left to right, so we can always start with that, from left to right, the graph is increasing, and that's the only part we'll have to say about that. So it's not decreasing anywhere, it's increasing the entire time. So the graph is increasing and crosses the x-axis how many times? One time. Okay, which means there is one real zero. Okay, and depending on what your graph is, it is possible to have no real zeros. That is possible. Okay, if there's no x-intercept, then there would be no real zeros. Okay, questions for me on that part? All right, then let's look at example 5. So example 5 is a story problem that we're going to have to interpret. So it says the cost of manufacturing a certain product can be approximated by f of x equals 3x cubed minus 18x plus 45, where x is the number of units of the product in hundreds. Part A says evaluate f of x, okay, for x equals 0 and x equals 200. Okay, so that just means I have to go to my function and I have to find what the value is when x is 0 and when x is 200. Okay, so we're going to start there. Okay, so if x is 0, we can call that f of 0. And then we're going to plug that in for x into our equation. Now with 0, we can do this one without a calculator, right? Because what are we going to be left with? 45. So f of 0 equals 45. It asked us to evaluate. That's what we did. Okay, now we're going to do the same thing with 200. You are going to get a large number, so don't be alarmed. So 3 times 200 cubed minus 18 times 200 plus 45. Okay, so I'll give you a minute to evaluate that, and then once you evaluate, I want you to start thinking about part B. Don't write anything down yet, but I do want you to start thinking about how you can describe this. All right, Dylan, what'd you get for your final value?
I got 23,996,445.
Great. Okay, and most of you found it just by plugging that all in, right? Doing your calculation. That's perfectly fine. Yeah, you're good. So this is your f of 200. Okay. All right, we evaluated, we plugged it in. Awesome. Now we're going to go to part B. And part B asks us to describe what the values of the function from part A represent. Okay, so describe what the values of the function from part A represent. Okay, so what we're going to do is we're going to have to go back and we're going to have to understand what this represents. So in order to do that, okay, what we want to interpret is we want to interpret the input and the output. So what this is asking us to do is we have to make sure that we include what the input and the output represent in context of the problem. What do the input and the output represent in context of the problem? Okay, so let's talk about the input first. Okay, let's talk about the input. First of all, the input is represented by what variable? I heard a couple people say it. What is it? What's the input? What do you plug into the function? X. Okay, so your input is your X value. Okay, let's go back to the description. Does it tell us what X represents here? Yeah, what does it say? The number of units of the product in hundreds. So I'm going to highlight that. That's important. Okay, especially the fact that it's in hundreds. I'm going to put a cloud around the hundreds because that's going to be really important. Okay, so the input is the number of units measured in hundreds. Okay, now let's talk about the output. The output, and leave a little space because we're going to do something else there. Okay, so the output is represented by what variable? Yeah, f of x. Good. Okay, and it does tell you what f of x is, right? The cost of manufacturing a certain product can be approximated by, so the output represents what? The cost. So the cost of manufacturing, and the cost is measured in what? If it doesn't say, it's going to be dollars. Okay, so now we're ready to talk about what f of 0 equals 45 represents. Okay, so if it's f of 0, the input is 0, that means how many units am I manufacturing? None. So this f of 0 would be the what? For some of you in physics? Really? In physics, they talk a lot about like the initial value, like the initial velocity. When you are plugging in 0, that is going to be your initial cost. So if no units are being made, okay, what could be something your initial cost could be for some type of business or manufacturing? If you don't manufacture anything, what are you paying for? What is it? I sing here. So what are some of the costs of a business besides manufacturing the product? Yeah, you know?
Maybe the workers or the electricity they need for
Yeah. Maybe they have to pay for the space where they're going to manufacture it, right? Yeah, so the electricity, the lease space, maybe there's a machine, right? So whatever it is, it's going to be their startup cost, okay? So we're just thinking of this in terms of real life here, okay? So f of 0 equals 45 represents the initial cost before manufacturing any product which is, in this case, so we explained the initial cost before manufacturing any product, that's the input. The output tells us that that initial cost is what? $45. Okay, so f of 0 equals 45 represents the initial cost before manufacturing any product, which is $45. Okay? Now, the f of 200 equals 23,996,445. This represents that it will cost, so remember, the output is the cost, so it'll cost that 23,996,445 to manufacture how many units? Not 200. Okay, so yeah, so I asked you that on purpose because I knew it was tricky, right? So because this is measured in hundreds, okay, it's not 200, it's 200 times 100. 200 times 100 is 20,000. So the 2 and then the 4 zeros. So it will cost that 23 million to manufacture 20,000 units of product, whatever that product may be. Maybe it's the pound puppies I was talking about. Okay, so based on what they're measured in, that's what you're going to have to use to interpret the problem. Okay? So that's just something that you want to watch out for. If it tells you like it's in hundreds or in thousands. Alright, and then your 3.1 homework, I'm going to put that up from the calendar.